to Professor Sergei Gukov from Caltech. Sergei?
Yes, can you hear me?
Yep, yep. Let me try to share screen, or could you try to? Brilliant. Okay, something's happening. Oh, fantastic, fantastic. I can see you, and oh, good. I can see you. Brilliant. Great. So apologies that we're running a bit late. We got some announcements in the beginning. So we're very happy to have Sergei Gukov from Caltech, who's going to tell us about machine learning and knotting. So over to you.
Well, thank you, Yang. And since this is the very last talk of this marathon, I want to take this opportunity to thank everybody who was involved in putting it together, especially Yang. So thanks a lot. This is fantastic format. And as you suggested the other day in one of the talks, maybe even 3 weeks is a reasonable experiment to try next year. So I had a lot of fun and enjoyed the meeting so far. So really great format, and thanks again for organizing it. So I also want to mention Chengming Bai, a director of the Chern Institute, and again, everybody else who helped in putting it together. So maybe virtually, or actually let's give them a round of applause. So thank you. And I'll tell you about work we did last year with Jim, Fabian, and Piotr, and it's on the interface of machine learning and mathematical sciences. But perhaps to put this talk on a broader perspective, I want to mention that, of course, our colleagues in other disciplines, especially more experimental in nature, have been using AI for a long time. This concerns, for example, experimental particle physics, as many of us know at CERN and other colliders, especially in analyzing data. AI has been used for a while in biology, in various other sciences. But it's interesting that in theoretical sciences, it wasn't used as heavily until recently. And perhaps one place where it naturally started propagating into theoretical research is in cosmology and astrophysics, because the line there between experiment and theory is a little bit more blurry than in other disciplines. And for instance, this is one of the papers on this kind of interface going into theory from CETA. It's one of the strong places in theoretical astrophysics in the world. And here, back in 2014, it doesn't use super sophisticated machine learning. It's basically based on support vector machines. But since then, there has been a lot of development and also propagating in more mathematical areas, such as string theory and study of Calabi-Yaus. And many people who participated in this symposium actually contributed to this development. This is just a small sample of various developments that happen over the years. Some of them go quite far into mathematical realm, so way beyond theoretical physics. And this is actually a fairly new trend. And even though I won't give you a historical perspective, I want you to perhaps take a note of a timeline. So on the last slide, the date was 2014, and most of the developments shown here happened within past 5 years or so. And this is actually great news. It means that the development is very fast, fairly recent, and also the same timeline of about 5 last years. You'll see several in several other places in the talk. So it's actually curious to make such connections and perhaps see hints why this rapid development is happening and where we're heading. So speaking of where we're heading, I think it's also good to reflect as our field matures by the field, I mean interaction of AI and mathematical sciences, I think it's good to aim or try to formulate big challenging questions which would make a big splash and that would position this entire field firmly among other tools, techniques, and areas that we use. And for this, we need a killer application. So even before we start applying AI or ML to different problems in mathematical sciences, it would be good to come up with a clear, well-defined problem where we all can agree, even before doing this computation, that solving this problem will definitely make a big splash. As Caltech, we would call it home run, something that would make a front page of Nature or Scientific American or something like that. So to formulate this problem, or when we think about this problem, and it's actually not so easy to come up with a well-defined, clear problem that would satisfy this criteria. Well, what kind of problem should it be? It should be something that has a very clear answer in the end game, like yes or no. It shouldn't be just incremental improvement by AI, but it should be a very clear yes or no kind of win or lose end result. For AI to be useful, it should have probably fairly large state space or configuration space, which is why it may be hard to analyze by analytical or human effort, but it should have fairly simple rules of the game so that machine can hopefully win this game. I'll be honest that in this talk, of course, I'm not going to give you a solution to such a big problem. And in fact, I find it really challenging to think of such problems which satisfy this criteria in mathematical sciences. If you have ideas, I think it would be extremely useful to brainstorm and try to formulate these goals. But I will give you one example of such problem which fits the bill, and if solved, hopefully would definitely make a kind of front pages of main magazines and feels like a game analogous to, for example, game of Go or game of chess, where we know that artificial intelligence now can easily beat us human. In fact, this comparison between doing scientific research and playing the game of chess or game of Go, the Asian chess, as it's sometimes called, is not new. At Caltech, where I come from, legacy of Richard Feynman is still very strong, and he liked to compare doing scientific research to watching the game of chess as if you don't know the rules, but see how pieces move. And from that, our job as scientists is to figure out what the rules of the game are and eventually learn how to play the game. So this is indeed, as you can see, a very nice quote and very close parallel to how machine learning would also approach this task. And by watching several games, or probably many rounds of games, finally learn the rules and even learn good strategies, tactics, and so on. So for trained expert, looking at a chessboard like this reveals a very rich story. So this is not just a random chessboard. In fact, those of you who play chess will quickly recognize what the situation is here, what's going on, and why this board is famous. To a beginner, of course, it looks pretty random and may not tell as a rich story. And this is exactly the same kind of thing that machine learning is good at. It's by learning the rules of the game, it can reach the same or follow the same path, roughly speaking, as a beginner chess player goes into grandmaster by learning different combinations, going through many chess boards, and finally reaching the level where a board like this is actually easy to interpret. So the problem that I'll offer looks kind of similar. So here is a picture of a particular knotted piece of string, and the question is very simple. Can it be reduced without tearing it apart in three-dimensional space to simple unknotted circle? And as I'll show you in the next slide, it's basically a very simple problem with very few rules of the game. So the rules are extremely simple, but configuration space is so rich that it's actually hard to answer this question. So mathematically, this is unsolved problem, and an important one, the kind of problem that would make covers for reasons that I'll explain in a minute. But here I want to compare this with the game of chess, and also with the way how, again, to untrained eye, this particular example, for instance, may look totally random, and it's hard to say if it's knotted or unknotted. But to a trained algorithm, in fact, the one that we studied with Jim, Fabian, and Piotr, this actually tells a fairly rich story, and algorithm can easily say yes or no. So in this kind of problem, when you see a picture like this of a knotted string, there are only three rules that you can employ. These are called Reidemeister moves. And basically the question is, if by using the same rules, these three rules, you can reduce the picture on the previous slide to the unknot. Notice that the rules are much simpler than in the game of chess, but again, configuration space is huge, probably somewhat similar. So the reason this silly looking, fairly easy to state problem is quite important, and if solved, would make covers, is because this is basically the key ingredient in the smooth four-dimensional Poincare conjecture. So the Poincare conjecture, which is the only unsolved version of Poincare conjecture in dimension 4, is asking whether homomorphic four sphere, four manifold homomorphic to four sphere is actually a diffeomorphic to four sphere, namely four sphere itself. And the way four manifolds are presented is precisely in terms of such knotted diagrams. So they're called Kirby diagrams, and an example of an actual Kirby diagram, which might be relevant to smooth four-dimensional Poincare conjecture, shown here. It's taken from a nice paper by Mike Friedman, Bob Gompf, Scott Morrison, and Kevin Walker, where they did try to use computer techniques to assist with the four-dimensional Poincare conjecture. They didn't use machine learning. This was just completely classical, normal computer work. But the type of diagrams that appear, these knotted diagrams, are indeed real. And what I want to emphasize here is that they're quite busy. So this looks like a very busy subway system, maybe not in London, but in a fairly large city. And this is indeed the whole point, that the smooth Poincare conjecture, even though it sounds very fundamental and has many connections to various other areas in topology, its counterexamples are usually just this knotted type of diagrams, and question is whether they're knotted or not. So that's really it. The only problem is that they involve so many crossings. Typically, interesting examples start with 30, 40, 70 crossings. So in their paper, the techniques that they used required understanding knotted diagrams with 170 crossings. So these are typical numbers. And the problem is that by analytical techniques, no matter whether you use John's polynomials or other tools, you usually reach a ceiling of about 10, 15, 20 crossings. And that's it. It's really hard to go by any analytical or traditional computer techniques beyond 20 crossings. So that's why we need to, in order to go in space in this field and break out from stratosphere, we really need to go beyond 20 crossings. That's the goal. In fact, quite far, by order of magnitude at the very least. So close cousin of Poincare conjecture is a relative Poincare conjecture, which instead of a four sphere is asking the same question about the ball. And normal ball looks like a picture here, but an exotic one, the one which doesn't have the standard smooth structure, would be non-diffeomorphic to a standard ball, would not have a smooth radius function. So that's one way to think about it. And it is this relative version which was actually relevant to the paper of Friedman that I just quoted, because another question that one can ask is whether a knotted diagram drawn on a boundary of the ball can be bounded by a smooth disk. So I cannot visualize it in a four-dimensional space, but this is a picture which shows bounding knots in a three-dimensional space. That's a somewhat different question, but analogous to the real one that we want to ask here. And this question, whether a knotted diagram can be bounded by a smooth disk, is actually also a variant of this unknottedness problem, because it can be formulated by the concise set of rules. In fact, pretty much same set of rules as we saw before, plus a couple of more. So again, it's of the same type, that you're presented a very complicated knotted diagram, and you have to answer a yes or no question using very few concrete rules. So it fits perfectly the profile of game of chess, the game of Go, and other games that machines can easily solve. So first question, if you really want to try to approach it with machine learning, is how you encode the data of the knot in your algorithm. There are many ways to do it, and if I have time, I'll show you another one. But the one we used is where a knot is represented by a braid, shown on this slide on the left part for each knot. And braid basically consists of basic elements. You can call them words or letters called sigma 1, sigma 2, and so on. They represent whether you're braiding ith pair of strands with positive or negative twist. And then again, there are very few rules which express equivalences analogous to Reidemeister moves. For example, if braiding happens at positions which are far from each other, then this words or letters commute. So when you write it in terms of sigmas, the generators of so-called Artin braid group, then you can just move them past each other. If they happen to be next to each other, they obey the analog of a Reidemeister move, the interesting Reidemeister 3 move, and this is the interesting braid relation in the braid group. And that's more or less it. Apart from that, there are no rules, and therefore each braid whose closure would give us the desired knot, therefore would be written as a sequence of letters or words, sigma 1, sigma 3, sigma 1, sigma 4 inverse, and so on and so forth. So therefore, you can say that you're basically presented with a string of words or letters, and therefore you need to tell the meaning of the sentence or part of text, namely whether it's trivial or not, based on this dictionary or equivalence relations. So as you can see, the way I presented this description of knots in terms of braids is very analogous to presenting a text in some foreign language. In fact, those of you who are not very familiar with knot theory probably look at this, and it does look kind of like a foreign language. But again, the point is that it has words and letters and plays by the same rules. So speaking of machine learning and artificial intelligence, we can therefore try to ask our colleagues in natural language processing or natural language understanding if they have the right tools for us to study this problem. So this subject actually goes back quite a while. So this is a conversation between a machine and a man, that a person and a computer, that happened exactly 50 years ago. In fact, it's one of the very first natural language processing algorithms, and for one of the first AI systems. So maybe we should have a little celebration for this machine. And as you can see, even back then, 50 years ago, the conversation is fairly reasonable. So the person is asking, what is the pyramid supported by? Computer says the box. How many blocks are not on? How many blocks are not on the box? 4 of them, and so on and so forth. So it's a fairly decent conversation, and it seems like machine is understanding the meaning fairly well. But again, it's only one of the first, and its inventor is Terry Vinograd. So he's one of the founding fathers of the subject, and the name of this machine is shown here on the slide. I'll let you Google it and see what this name stands for and how it came about. But in any case, Terry developed it back in 1971 at MIT, and then he moved to the West Coast, where he continued his research on NLP and natural language understanding, and had many successful students. So here is one of them. You all know this guy, and he's famous for many things, including the PageRank algorithm and so on. And one of the things that Terry Vinograd anticipated already at early stages of the subject is that as AI systems develop and become better and better, one should produce interesting examples that would challenge AI systems and tell us, or will allow to test how well they understand the text. And now this interesting kind of knotty problems in language understanding are called Vinograd schemas after Terry Vinograd. So here are a couple of examples, and later I'll show you a few more. Say there is a sentence that you want to understand and perhaps translate in a different language. The trophy would not fit in the brown suitcase because it was too big. And we all immediately can understand what was too big and what was too small in the context of the sentence. And this is important because if you want to translate it into different language, for example, or understand the meaning of the sentence as in our node problem, you really have to be clear about it, because, for instance, in translation to a different language, trophy and suitcase may have different gender. And you have to be fairly accurate about it in order to have good translation. And then in the bottom of the slide, there is another example of it. And again, later I'll show you a few more. So fast forwarding through from 1971, in 90s and early 2000s, most of the machine translation was based on probabilities. So these are so-called statistical machine translation models. And they all typically consist of 2 components, one of which is a translation model that's responsible for understanding the meaning, and then a language model, which is responsible for producing analogous, nice sounding sentence in a different language. And shown here is evolution of this statistical machine translation, in fact, different kinds shown in red and blue over the years, and how around 2014, a neural machine translation, NMT, is starting to take over. So this transition was pretty fast, and it started in 2014, but already by 2016, Google Translate completely switched from statistical machine translation that they used until that point to neural machine translation. So development was very, very fast. And just like most SMT systems, some of the early neural machine translation models are based on 2 components. Here, they're represented by encoder and decoder RNNs. So these are roughly analogs of translation model and language model in SMTs. And each part is responsible for its own task. So the encoder RNN, or it could be more advanced long-term memory unit, basically takes input sentence and tries to understand its meaning, and then it's giving the meaning vector to decoder RNN, which is producing the resulting new sentence in a different language, here from English to German. And those of you who know German can quickly see that this meaning is not quite accurate. So the sentence we're trying to translate is, you asked us to call you back after last Friday, and the translation, roughly speaking, sounds, however, we hope to help with your travel plans. So that's not exactly what the original sentence is, and there are such hiccups. And the reason they happen are, there are several reasons why such things happen. So first, in this architecture, which is seq to seq, sequence to sequence, the translation is sequential, and the difficulty is that you cannot easily go back and correct if you made a mistake somewhere halfway along the translation. So this is related to long-range dependencies and trying to keep the meaning or context over a long range of text. So in physics language, you need long-range correlation functions. So also such systems often make up information, for example, the gender, if gender was absent in English sentence and in German or French words have gender, so therefore you have to get it from the context. This is also something that's was notoriously difficult in this seq-to-seq machines. Also, if you're trying to translate a large chunk of text, then you're basically composing activation functions and get vanishing or exploding gradients, which is another problem of translation of larger chunks of text. So many of these basically cry out for better understanding of the context, and this was one of the main challenges in early days of NMT. Again, back around 5 years ago, notice that roughly same timeline as explosion of interest in the subject happened in mathematical sciences, and then perhaps there is a correlation here. So these are some other examples of, again, peculiar or funny mistranslations. Again, those of you who speak native languages can probably understand better than me why this happened, but I already gave you a couple of reasons why. And nice solution to this entire set of problems that I just mentioned actually came from computer vision. And this advance also started in 2014 and is called attention mechanism. So then it quickly propagated in first in statistical machine translation and then in neural machine translation, where the idea is that as you keep translating long sentence or a long chunk of text, you actually keeping track of relevance, namely this is by definition the dotted product of keys and queries, the input and context, and as a result, you're maintaining some sort of meaning over a long time. So here the sentence is very short, of course, but this kind of mechanism works very well even on long sentences. So here is an example where you don't do translation, but you do parsing from a longer sentence. You're supposed to produce a shorter one, and as you can see, in this case, the longer sentence is Russian Defense Minister Ivanov called Sunday for the creation of a joint front for combating global terrorism. And the parse sentence is pretty good. It contains the meaning, retains the meaning fairly well. So this is an example of how this attention mechanism is working. And soon after, in 2017, there was a very nice paper which made kind of a small revolution in the subject, coming from Google Brain, and it's Allah is on a so-called transformer architecture, which basically builds around this mechanism, the attention mechanism that I showed you on the previous slide. So it scores extremely well on this blue score, which is the standard score that's used to measure accuracy of translation. Blue score of 20 something is what we saw here in all days. And as you can see, this paper quotes the blue score, which goes all the way up to 42 almost, which is quite fantastic for machine translations. It also does very well on this Vinograd schemas that I showed you earlier. And these are some other fun, amusing examples. I encourage you to take a look at the slides or Google them. Lukas Kaiser gives fantastic talks on this subject from Google Brain. So one of these Vinograd schemas is the cow ate the hay because it was delicious. And again, to translate it properly, in this case to French, you have to know who was delicious, the hay or the cow, and so on. So final tweak to this already spectacular AI system comes in a groundbreaking paper by Kitaifat et al. In 2020, just last year. This is not Alexei Kitaev, it's by Nikita Kitaev from Google Research and UC Berkeley. And it builds on Transformer to produce yet another architecture called Reformer. I'm not going to go into details of what improvements and introduces, but it's you can think of it as a glorified transformer, and basically that's the one that we used in our experiments. So then we apply this architecture and this natural language processing mechanism to try to understand the words made out of braid elements, this sigmas that I showed you before. And again, the goal is to understand, is the sentence trivial or can be reduced to a trivial one by basic moves of the game or not. And here is the one of the plots summarizing performance on this unknotting problem as a function of the braid length. So braid length is a number of crossings or number length of the sentence. And again, since we needed a mechanism that performs really well on long chunks of text, and for reasons that I explained so far, this was a good candidate, and indeed it performed really well. In fact, somewhat interestingly, it performed slightly better for longer chunks of text, or for longer braids, or for knots with more crossings. This is peculiar. I don't think we understand fully the reason behind it. We give several reasons in the paper. And one of them is that training with more interesting competitors or rivals, for example, in the game of chess, is teaching you how to play better. And maybe that's what's going on here. As you see more complicated knotted diagrams, longer braid words, you basically learn how to interpret this better. And for our reasons, this is good because remember, for smooth Poincare conjecture, one really needs long braid words. One really needs knots with many crossings, more than 20. Ideally something like 70, 100, or 200. And here, this looks very promising. So we didn't attempt to solve SPC4 in that paper yet, but it definitely is a good sign that AI can be very, very useful here. And indeed, we are trying to approach SPC4 in our current work. Here is reinforcement learning applied to the same problem. Indeed, you can ask not just yes or no question, whether machine can recognize, neural net can recognize whether the diagram is knotted or unknotted. This is what's shown here, but you can actually ask a machine to find the moves that do the job, namely how to play the game. And again, we tried several different algorithms, several different architectures to tackle this task. And green dots are random walker. So as you can see, its performance is very poor, and as the number of crossings or length of the text gets bigger and bigger, it's really poor. And the one that performs really well here is represented by the blue dots. This is the TRPO algorithm, trust region policy optimization. So if I were to compare it to more familiar, more standard algorithms based on gradient descent, or in this picture on the left, gradient ascent, then TRPO is a very conservative way of exploring the region around you and then making decision where to go just within this small region. So for instance, if our goal is to scale a mountain, namely perform gradient ascent, then as the picture on the left illustrates, you may decide that the best move for you is to keep walking in a certain direction, but you may fall off the cliff, and then again, AI system may never recover if it's a big fall. So this is one potential problem, but TRPO, in contrast, does the following. It starts at a given point, and even in a landscape with sharp gradients, it performs really well, because within certain radius near that starting point, it explores what is the highest point, what's the most optimal way to go, moves there, and then repeats the process. So that's basically what TRPO does. And in this plot, it shows a number of various actions or steps that is needed to unknot an unknot, if it's unknotted circle, as a function of number of crossings. So as you can see here, we go all the way to basically 100 crossings. So that's really good and really promising for this next project of trying this kind of techniques, AI techniques for SPC4. And the TRPO, for example, does really well because its number of actions stays reasonably modest compared to average number of steps that random walker does, for example, and other mechanisms. So this is just to illustrate that reinforcement learning actually learns something. So that's a comparison of trained and untrained neural net. But I want to end this short talk by advertising another good problem that I think is well suited for machine learning and mathematical sciences. There's this interface. It has, again, kind of same appeal as game of chess and many other problems of this kind. It's not as ambitious as smooth four-dimensional Poincare conjecture, although I think it's good to brainstorm such problems, but a kind of problem that came in the process of this brainstorming. And it's based on a correspondence, which until so far is still fairly mysterious and predicted by physics, that to each knot, in fact, same kind of knotted diagram as I showed on previous slides, you should associate a quiver. That's a diagram represented, illustrated on the right part of the slide here. And both knot and quiver, even though they seem quite visual, they're actually combinatorial pieces of data. So knot can be encoded either in this length of text, string of text, the braid word, or by a string of integers, such as Gauss code, as shown in the bottom of the slide. And similarly, quiver is basically a combinatorial piece of data represented by a bunch of vertices and arrows going from vertices from one vertex to another, and that can be encoded in this adjacency matrix C shown below it. So therefore, the problem really is easily encodable in a sense that you have to go from one combinatorial data to another type of combinatorial data. And the beauty of this question is that physicists and mathematicians, including the pioneers whom I showed on the previous slide, predicted that such correspondence should exist. They also worked out lots of examples for which there is a known quiver for a given knot. And this includes many infinite families and probably many knots up to 10 crossings or so. But in general, the rule is not known. And the question how to find this correspondence or what are the patterns and so on is wide open. So that's why I think it would be extremely interesting to try to apply machine learning and various techniques to this problem of trying to associate a quiver to a knot. And with this, I want to conclude. Thank you for your attention. And again, thank our organizers and especially Young for arranging this marathon of very interesting talks.
Thank you very much, Sergei, for that beautiful overview and talk. So I'm sure there are many questions. Would anybody like to fire up?
I have a question. Hello, Sergei. This is George.
Hi, George. Nice to see you.
Wonderful talk. Many great things that I didn't know about. And let me ask about one that you mentioned that was fascinating, the connection between knots and languages, right? So is it, I mean, there are two natural questions here. The first one, okay, maybe naive from your point of view, because you have thought more deeply about this, is some aspects of knots, right, we can describe from the Chern-Simons theory, at least some, like the Jones polynomial, etc., right? And so is there some way to think about such invariants, quote unquote, I don't know if I want to call them, such as Jones polynomials in the context of languages? That would be the first question, if that makes sense. And the second one, if there is a knot quiver correspondence, and you can think of knots as languages, is there some way of thinking of languages or issues in languages from the point of view of quivers? Do these questions make sense to you?
They do. So let me try to answer, but again, feel free to correct me or elaborate if you want me to go in some other direction. So regarding Chern-Simons theory, Jones polynomial, maybe a couple of comments. So first of all, the most naive attempt to try to solve this unknotting problem with the Jones polynomial or Chern-Simons theory, even though Chern-Simons theory offers many variants of Jones polynomial, it's really tough because computing Jones polynomial is extremely challenging. So in complexity theory, this would be really NP hard, if not higher complexity class. So in comparison, we actually don't know the complexity class of this unknotting problem. It may be P. So it actually has to do, it has many interesting connections. This topological problem has many interesting connections to P versus NP. And it's known that this problem is an NP class. It's also in co-NP class. And there is a chance it may actually be solvable in polynomial time. So we just haven't found the algorithm. So that's another reason why this problem is appealing from computer science perspective. Now, looking at Jones polynomial from a language analogy, I would say that it basically encodes some piece of information about the text, which, for example, if you have two strings and Jones polynomial happens to be the same, it's telling us about certain symmetry of or certain equivalence of this chunk of text. And this is actually interesting connection that has been explored somewhat. For example, some of our speakers in this program looked at symmetries in the context of AI. But it's interesting that it required somewhat, I mean, it's somehow traditional AI experts in Google Brain and people who would actually be closer to AI thought only a little about the role of such symmetries and equivalences. And by now, this is fairly active field, and Sven, Jim, and many others, Fabian, have thought about it. And I'm really glad to see them pioneering or basically almost leading these directions, because the role of symmetries or equivalences in AI is, again, very, very rich field. And that's basically what you're asking with this question.
Yeah, yes.
So I think it's a fantastic area. I have a little less to say about not quiver correspondence in this context. In part because so even though this quiver is associated to knots, they actually come from, they encode some of the data of not quite John's polynomial, but they're related to various categorifications like Kovanov homology and other things. So there are some connections to invariance, but in the end of the day, this data over quiver is such a simple combinatorial data that once the dust settles, in some sense, it's very nice residue of this homological invariance, and invariance already disappear from the picture. So I'm not even sure if in this AI challenge that I'm presenting here in the slide, thinking about invariance is going to be useful. Again, partly because computationally they're extremely hard to compute. It's hard to move beyond roughly 10, 15 crossings. But again, maybe I don't want to say no, because maybe further thinking will lead to some good ideas. So I think it's a good question. I apologize that I don't have much.
No, that was wonderful, the elaboration. Thank you very much.
Thank you, George.
Thank you.